already at the end of last lecture learned a little bit about stability in terms of the Nyquist plot, because when we talked about encirclements of -1, we're talking about stability there. We're going to get a little bit more in depth on that, though, in this lecture. And so that's why it's called stability from the Nyquist plot. Stability from the Nyquist criterion has established closed-loop stability for unity controller gain. Of course, we would like to learn about the stability for any value of gain k and the closed-loop transfer function g over 1 plus kgh instead of just g over 1 plus gh. We want to know about stability that changes with the gain and the feedback loop. So, as we did in root locus, when we would so root locus is the location of the closed loop poles for various values of gain k, right? So we learned there that we lost stability when the poles that were in the left half plane moved over into the right half plane, and we lost stability. We don't have that interpretation here. Of course, with a given system, you could either look at it from the root locus perspective or from the Nyquist perspective, the frequency response perspective. So we're looking at it from this perspective now, and we're going to try to think about stability in these terms. So the Nyquist plot is of, as you may recall, GH of gamma n, where gamma n is the contour that encircles the right half plane, right? And GH is the open loop transfer function, which is to say the forward path G and then the return path H multiplied together. And if we include the gain, so if we had a controller that was just a gain in the feedback loop, then it would be KGH of gamma n. So the question is what changes if we stick a gain in there? Is all bets off from our previous analysis, or is it related? And it turns out it's related in a very simple way. The gain just stretches this contour image by a factor of k. So it just expands it about the origin outwards. And it's pretty easy to see that. If you multiply a complex number by a gain, you're gonna multiply the real component and you're gonna multiply the imaginary component. So if that imaginary number was at 1 plus j1, right? So in the complex plane, 1 plus j1. If you scale that by a factor of 2, you're going to be at 2 plus j2, which is to say same phase, but you just stretched the point out by a factor of 2. You expanded. So if you have a bunch of those points, a collection of those points that is a contour, then you just stretch it out. So our Nyquist plot stretches out if we multiply it by a gain, or shrinks if you multiply it by a gain less than 1. So you can do that too. I often think of it as stretching, but you can also shrink. Okay, so recall that for stability, we are concerned with encirclements of -1. Remember, we went through that lengthy argument. -1, which is on the real axis, right, in the left half plane, we are interested in the number of encirclements of it. And that is going to be critical for stability purposes. So scaling k can change the number of encirclements. So we can scale this whole Nyquist plot. So maybe with a certain scaling we have no encirclements, and then with a certain other scaling we have 2 or 4 or 18 encirclements. For instance, let's consider a system with open loop transfer function 7.17. So this is our transfer function, open loop transfer function. This system has 0 poles in the right half plane in the open loop system, right? So GHS equals -3 is a pole and -5 is a pole. So they're both in the left half plane. So there are no poles in the right half plane. So P is equal to 0. Thus, for no encirclements of -1, the closed loop system is stable by the Nyquist criterion. Okay. Figure 7.5 shows the Nyquist plot for 3 different values of gain k. So that figure is here. So if the gain is just 1, then we have this Nyquist plot, and it's stable. And if you have it on the other side, so if you scale this thing up, k is 4, scale it up, notice it stretched the whole thing out, and now you have 2 encirclements of -1. And the direction of those encirclements is important. And so let's interpret. So it's stable for n equals 0, no encirclements. So z is also equal to 0, and the closed loop system is stable. If k equals 4, the system this stretches the previous plot by a factor of 4. There are -2 counterclockwise encirclements of -1, which is to say that there are 2 clockwise encirclements of -1. So if you come here and you look at, what I always do is I start at -1 and I draw a ray out. In any direction is pretty valid, but you want to be able to make sure that there's it should be valid in any direction. But the opposite is not true. If you can draw a ray that doesn't intersect anything, you have to draw that ray. So that's important to remember. So like you could have, for instance, in this one, you could have a ray that you draw from here that intersects the blue one, right? I don't know why this keeps going back. It intersects the blue Nyquist plot, but you didn't have to, so you shouldn't do that. But in this one, you have to cross, if you're going to go outwards, you're going to have to cross 2 of these. And if you think of this ray as being like a hand on a clock, if it follows the direction of the arrow, then it's either going to go clockwise or counterclockwise. So this one here, the arrow is going this way. So this encirclement there is clockwise, right? And then this encirclement here is also clockwise. So it's 2 clockwise encirclements, which is to say n equals -2, because n is the number of counterclockwise encirclements of -1. So since this is 2 clockwise, then n equals -2, -2. Okay. So z is then equal to +2, and the closed loop system is unstable. Okay. So if you increase the gain high enough, your system actually goes unstable. If it's low enough, then it's stable. And then this sort of point at which the encirclements change from 0 to -2, which is to say when this intersection of -1 occurs, that is marginal stability. That's when it crosses over from stable to unstable. So if we're thinking on a root locus plot, this is where we cross over the j omega axis, right? Okay. So that's stability in terms of the gain, which is I think it's pretty straightforward in the sense that for a given system, you can scale up with the gain and shrink down with the gain. You may or may not be able to make something stable, changing the gain. If it's unstable to start, you may or may not be able to make it closed loop stable. If you make it closed loop stable, there might be some gain at which it will go unstable. It might start out stable like this one did with low gain and then go unstable if you do the feedback loop. So there are lots of possibilities, but I think that they're all sort of captured in this idea of stretching and shrinking down the Nyquist plot to change the number of encirclements. So let's talk about stability from the positive j omega axis alone. It turns out we can determine stability from the image of the positive j omega axis alone due to the real axis symmetry of the poles and zeros of transfer functions. The image of the negative j omega axis is simply a reflection about the real axis of the image of the positive j omega axis, which we mentioned, we noticed that before, right? When we did our Nyquist plot, we did the positive j omega axis first, and then we went around the big infinity loop, right? Which all happened magnitude-wise at the origin, just phases were changing. And then we went up the negative j omega axis, and we discovered that it's just the mirror image of the positive j omega axis. Yeah, nothing that occurs at zero magnitude affects stability, because you're never going to be encircling -1 when your magnitude is 0, right? So that whole infinity part of the contour that we mapped always ends up hovering around 0 and just changing phase, right? But that thing could go in like 50 circles. It's irrelevant to stability because the -1 is over here. So you can be doing circles over here and it's never encircling -1. So that's convenient. So the negative j omega axis does matter, but it's just a reflection of the positive j omega axis, and then this big arc that we mapped to the origin doesn't have an effect on stability. So we can find stability from just the positive j omega axis, and then knowing that we just flip it for the negative j omega axis. The same is true for that which occurs at infinite magnitude, which never intersects the negative real axis. And so that one's a little bit more subtle, but if you go through the argument, and it is also true for poles and zeros on the j omega axis, as this footnote discusses. So we can get away with just working with a positive j omega axis, and the Nyquist plots that you get in MATLAB or Mathematica, they are usually of the plus and the minus j omega axes, and they just ignore everything that happens at infinity and that happens at 0. And the reason they do that is it is irrelevant for the stability of your system. So, and what people are looking at those for is for stability. And it's hard to represent, too, what happens at infinity, what happens at 0. So they just ignore that stuff. And the way they plot those things is they aren't finding an analytic thing. They're just doing a numerical calculation, just like they do for the Bode plots. I mean, they're just calculating points and then drawing a continuous curve through them. So. And that's why, like, I'm pretty sure. It's over here. When I made this plot in Mathematica, I didn't make it in Mathematica. I made this in TAKZ and LaTeX. But anyways, this is something that is pretty easy to plot yourself. Like you can just calculate all these points. It's not that tricky. Of course, that's because we have computers doing all of this for us. And when these things were developed, all these ideas were developed without computers being a big part of it, especially this frequency stuff, because this was developed before root locus. So not a lot of access to computing back then. So this was a lot of hand calculation stuff. So graphical ideas, like when we talk about scaling, it's like for an intuition. We talk about scaling it up or scaling it down. We can just plot it and see what it looks like, right? And we vary the gain. We need to know that if you increase the gain, it stretches it, and decrease it, it shrinks it. But they might actually have like a scale out. Plot it at 1, k equals 1, and then like literally scale things out to do your calculations. So that's why a lot of the stuff started out graphical, and it remains so integral to controls. Like this graphical stuff is such a deeply rooted aspect in controls. So it's not just this Nyquist stuff, but also the root locus stuff and the Boda stuff. It's just deeply embedded, and so we're never getting away from it. I think it's a good use. I think it's they're good tools. They're still useful for us today. I just don't focus that much on the hand sketching of things because might as well have them do it. You need to understand how it works, right? I got to keep plugging that. So, gain margin and phase margin. So these are two things. Like, so who's heard these terms before thrown around? Gain margin and phase margin. So like, yeah, a couple of you have heard of it. This is another topic that is one of the fundamental ideas in control theory that you hear a lot about. So yeah, you're going to hear about root locus stuff, stability, closed loop poles, all of this stuff comes up. And gain margin and phase margin are two other concepts. And we're ready to define them now, finally. We understand why. We could have defined them in terms of Boda plots, but that wouldn't have made as much sense until we got to Nyquist. So, let us consider a system with a Nyquist plot for which smaller values of gain k yield a stable closed-loop system, and higher values of k that yield one that is unstable. So that's just like the one we just looked at, right? The one we just looked at for low gain was fine, for high gain, unstable. We saw that a lot in root locus analysis too, right? A lot of times there's these poles over here that when you go to high gain, they come over to the right half plane, and then we're in trouble. So it turns out that these types of systems are very common. We know that the key to stability in such systems is the number of encirclements of -1. We are now ready to define two key quantities, the gain margin and phase margin. For a given gain k, these parameters quantify how stable a given system is. Okay? The gain margin, gm, is a logarithm of the distance from -1 to the Nyquist plot's negative real axis intercept, -1 over a, as shown in figure 7.6. Blast, that's on the next set. So I'll load those in and show you the figure. And yes, I did just say blast. I don't think I've ever used that term before, but apparently it just made sense today. It's not that one, this one. 3 pages. 3 pages. Okay, so this is the figure. And this figure shows the positive j omega axis, the positive j omega axis mapping here. And we know that there would be a symmetric mirroring of that if we were to fill in the other side, right? So now we're so developed we don't even need to draw this, but we're going to do it here just to be fancy. We'll try to. So anyways, it's a mirror image, right? And this has a direction. We should be careful with that. Okay, so I'm going to delete this for now because it gets in the way of my writing. But we've got a definition now. And oops. So yes. So the gain margin is a logarithm of the distance from -1 to the Nyquist plot's negative real axis intercept -1 over a, as shown in this figure. So if we go to the figure, we see that the distance to this point is -1 over a. I'm just calling it that. Okay, calling this -1 over a. This intersection here, this intercept with the real axis, and specifically then in dB, typical manner of expressing the gain margin, we express it as 20 log base 10 of a. Okay. And that's the definition of it. And we said that it has to do with the amount of stability that we have, right? So if a is large here, that means that we're going to have -1 over a large number, which is going to, if a is large, we're going to be intercept of our real axis like back here, right? And if a is small, we'll be intercepting it out here. So a determines where this is, and large A means we're down here, and small a means we're down out here. And we said that a lot of systems are stable for low gains and unstable for high gains. And so what's happening is just what happened in that previous example that we did. We're going from not encircling -1 and having no open loop unstable poles. So we're stable for low gains. And when we stretch this out, we start encircling clockwise -1. And that gives us trouble for high gains. And then we end up with an unstable system. So the gain margin then, the larger the gain margin, the larger A, right? The smaller this intercept is, the more cushion we have for stability purposes, assuming it's one of these systems that behaves in this way, which I have said claimed is common, that these are common systems. So that's the definition of the gain margin, how much you can increase the gain before going unstable. Okay? Now, in a logarithmic expression. The phase margin is defined as the angle at which the magnitude is unity, so is 1, as the Nyquist plot approaches its negative real axis intercept -1. So if we look here, then as the Nyquist plot approaches this intercept, it crosses over the magnitude 1, so this unit circle here, it crosses through it, and there's some phase angle there. And the smaller this phase angle is, the closer, I mean, you can imagine if I was like out here coming through, if if I scaled this thing a little bit, then the phase margin would decrease, but also so would the phase margin, because that's going to be this angle, right? So as we get closer and closer, the phase margin is going to decrease as well. So it's another expression of how stable a system is. If you have a small phase margin and a small gain margin, that means that you're in danger of becoming unstable. If, say, some of your parameters changed, or if your gain was to increase much. So it's difficult to find mathematically, unlike looking at the Bode plot, or looking at the Nyquist plot for gain margin is just, where's this intercept, and then scaling it to b minus 1. That's pretty easy to do. The phase margin involves figuring out where this curving line crosses the unit circle and figuring out where that is, what that angle is. That's a lot more difficult to calculate by hand, at least. If you're going to do it numerically, it's not hard. But primarily for this reason, in a moment we will switch to a Bode plot representation, in which both the gain margin and the phase margin are easily found. So in Nyquist, gain margin is easy to find, but in Bode, both of them are easy to find, gain and phase margin. And we just need to make that leap from a Nyquist plot to a Bode plot and interpreting it. So that's our next step. As already mentioned, the gain margin and phase margin can be considered measures of stability. We consider this to mean that higher gain margin and phase margin correspond to greater confidence that the closed loop system will remain stable even under small changes to its system parameters. So that is the end of our discussion of stability with Nyquist, although it's going to keep coming back as we go forward towards design. But this was the sort of foundation.